So the first speaker, it's my pleasure to introduce Tom Hershowitz, who is, for those who know, a member of a very famous family of researchers. And so we talk about familial monads and structural operational semantics.
Merci, Nico. So hello, everyone. Is this working? Not anymore. Oh, yeah. Sorry. Okay, thanks. So thanks for being here. The starting point of this work is the observation that often in programming languages research, we tend to state our theorems for just one language. Typically, we come up with a brilliant idea, which we think of as widely applicable, but in the papers, often we illustrate it only on one particularly simple language, kind of the simplest relevant language for the idea to make sense. And so from a mathematical point of view, it's a bit disturbing, right? We would like to state the results for the family of languages for which they make sense. But there's a problem with that, is that as a community, I don't think we have a common answer to the stupid question of what a programming language mathematically is. So here are a few candidates, which I'm going to dismiss one after another, of course. So first, label transition systems. And indeed, we have plenty of general theorems about label transition systems. But there are some theorems that we cannot state within this framework, namely those about the interaction of syntax and the dynamics, right? Because transition systems don't feature syntax in general. A second candidate would be structural operational semantics in the sense of Plotkin, or maybe more precisely in the sense of some format. There's a whole community of formats. So that's good, but there's a whole class of theorems that we cannot talk about in this framework, namely those who talk about models, denotational models. And that's quite an important body of literature also. So we would like to be able to talk in general both of the interaction of syntax and the dynamics and of denotational models. So there is one candidate which allows us to do that, namely the functorial operational semantics framework of Turri and Plotkin, which has been much developed since the initial paper in 1997, I think. However, in a community, it's not yet used by lots of people, right? I don't think that any of you has ever published a concrete paper using the abstract results of bialgebraic semantics. So why is that? It's a bit disturbing. It's very powerful formalism using very involved categorical results, and yet the community doesn't use it in practical applications. So one possible reason for that is that the intuitions that you have when you do bialgebras are quite far from the operational intuitions. That's maybe debatable. It's just a feeling. Another possible reason is that often in programming languages, we use variable binding all the time. And bialgebraic operational semantics doesn't scale well to the setting with variable binding. It becomes very complex. And as far as I know, the last paper in bialgebraic operational semantics that covers binding dates back to 2008. It's actually a paper by Sam Staten, who should be in the other room now. And a third possible reason is a relative lack of expressiveness of bialgebraic semantics. For example, I don't think it can handle terms as labels. which you need, for example, when you do high-order pi calculus, or when you consider Abramski's applicative bisimulation, for example, for functional languages, when you use Howe's method, for example. So that's a problem. In summary, there have been attempts at a general theory of programming languages, but still there is room for improvements, so I'm allowed to try something new. So here's a tiny contribution, which I think is new but doesn't yet go very far. And the philosophy behind it is to be less ambitious. Namely, in bialgebraic operational semantics, you both have an abstract framework, an abstract language to talk about programming languages, but you also have a general machinery to construct instances of the framework, namely a format. Here, I'm going to focus on the first question, that of an abstract framework for reasoning about programming languages, and delay the question of formats for further work. So what are we going to do? We're going to abstract away from concrete classic notions, like the category of transition systems with functional simulations as morphisms. This, in the abstract framework, is going to be an arbitrary given transition category. That's a new notion. And then we're going to be able to define in an arbitrary transition category the classic notion of functional bisimulation, or even a bisimulation relation, by following the intuitions of pre-sheaf models. And then we're going to abstract over structural operational semantic specifications in the classic setting by giving a monad T on the considered transition category. I'm going to explain why a monad is like a source specification. And as a bonus, we get a notion of model, which is just a T algebra, an algebra for the monad. Then I'm going to state the main results, namely up to suitable hypotheses, bisimilarity is congruence, and bisimulation up to context is sound. Bisimulation up to context, maybe not all of you know. It's a technique for proving concrete bisimulations using smaller relations. It allows you to deal with much smaller relations. And I'm hardly going to touch upon this here for lack of time, but there's an extended case study in the paper about the pi calculus, which shows that the framework applies in the presence variable binding. So let's start from the concrete example of a very simple transition category, namely the setting where you only have one label. So your transition system is just a rewrite system, and the corresponding category is just graphs, so directed multigraphs, which means that you allow, it's a slight generalization, you allow several ways of moving from one state to another. So intuitively, I said that already. Then morphisms are just functional simulations. I'm not going to explain why, but it's really an easy observation. Now I need to introduce the following two examples of graphs, which are very basic. 0 is just the one vertex graph, and 1 is just the one edge graph. For those who know, it's just Yoneda stuff. And then the crucial morphism we need to deal with is the source morphism, mapping the one vertex graph to the one edge graph, picking up the source of the edge. Okay? Why? Because then we can define functional bisimulation by lifting. So we say that f here from x to y is a functional bisimulation when for all v and e making this square commute here, where this one is the source morphism, there is a lifting k making both triangles commute. So why does this have anything to do with functional bisimulation? Well, giving v amounts to picking just a vertex in x, v here. And giving e amounts to picking an edge in y. E here. And this V is mapped to F, mapped by F to the source of E. That's what commutativity of the square says. So we can draw E from F of V here. So on the right you have Y, and on the left you have X. And here F maps the left to the right. And K only picks up an antecedent of V, which starts from V. So here, normally you should recognize the definition of functional bisimulation, right? If the image does a transition, then you can find an antecedent in the source. So that's what the lifting property says. So now here's the general setting. Transition category is just a category with a class of distinguished cospans, which we denote by these letters generally, plus a few hypotheses, which I'm not going to delve into. You can assume like locally presentable, something like that. So then we let TS denote the class of all such source morphisms there. Yeah, the intuition is that these guys are the transition types. There could be several transition types. There are several examples in the paper also. So we can define functional bisimulations in the abstract setting by lifting exactly like before, except that here F should have the lifting property for all source morphisms in TS. And we denote that by this like orthogonality-like notation. Right, so now why do monads have anything to do with source specifications? A brief one-slide recap on monads. So a monad is an endofunctor, T, on your considered category, with natural transformations from the identity functor to T and from T squared to T, satisfying a few axioms. And each intuition you can have is that T of X is more or less like the set of terms with variables in X. Then eta, the transformation from the identity functor, just embeds variables as terms. And mu maps any term whose variables are terms to the term that you obtain by plugging the variable terms into the holes. Okay, so you start with a term in 2 layers, and then you forget where the layer was. Okay, so essentially a monad is like a term language. But in fact, it's a very general form of a term language. For example, you can view source specifications as monads. I think the idea of doing this is originally due to Sam Staten in his 2008 paper. So given a source specification S, what does the monad, the corresponding monad TS do on graphs? Well, you start from a graph X, then TS of X has as vertices the terms with variables whose variables are vertices of X, okay? And as edges, it has transition proofs according to the source specification you started with, but with axioms in X. So you can take as axioms edges of the graph, of the argument graph, okay? So the intuition is that you start from X and then you saturate it under the source rules that you consider. So there are a few slides then about operational intuitions in this framework. So for example, a transition proof in this setting is just a morphism in the Kleist-Lie category, which means a morphism of the form something arrow T of something else. For example, a transition proof with n transition variables, like a context with n holes, like a proof tree, which you stop at a certain level with in n branches. It's going to be a morphism from the one edge graph, to T of 1 plus 1 plus 1 n times. So plus here is coproduct. It means that you have copies of the one edge graph. A second example of an operational thing that you can do in this setting is plugging proofs into one another. So here, for example, you start from a proof pi1 of a certain transition from P to Q with the three variables x and y, assuming an axiom that x goes to y. Okay, that's the whole proof. And then you want to plug into this axiom another proof, for example, this one, which has two hypotheses, two axioms, that R goes to S. And then you obtain something like this, where X is replaced by R and Y is replaced by S. Okay? You take this one, you plug it in here. You get something like this. You can do this abstractly by composing in the Kleisli category, which means you take pi1 here, goes from 1 to t of 1, and then you take t of pi2. So remember, pi2 goes from 1 to t of 1 plus 1 because we have two hypotheses there. But because you're under t, you're working under t here, you arrive in t of 1 plus 1. Okay? Then you do mu, and you land back to what you wanted, a proof with two hypotheses. Okay? Now, I don't have time to do more, so I'm just going to state the results. Under suitable hypotheses, notably the familial hypothesis of the title, which I don't think I'll have time to explain, bisimilarity is congruence, bisimulation up to context is sound. So I think the second point here is the first abstract proof that bisimulation up to context is sound that applies to cases with variable binding. So as an example, as I said, as an example application with binding, we reprove known results about pi calculus, namely that bisimilarity is a non-input congruence, which means that it is preserved by all constructors except the input prefix. And bisimulation up to non-input context is sound also. It's a similar result. So this demonstrates the flexibility of the approach because normally you start from the source specification. The T algebra that you consider is the free one, T of the empty object, the initial object. But here, in order to make sense of these partial results, you need to consider algebras that are not initial. So I don't have time to explain this. That was about familiarity. So conclusion, perspectives. There's a lot to do here. First idea is to consider existing formats and show that they generate instances of this new framework that would easily extend the applicability of the approach. But we could also consider more categorical formats using the theory of free monads and that kind of stuff. Also, we can, on the other hand, we can develop the framework in itself, like prove more results in it, considering weak variants of the bisimulation methods, process equations, environmental bisimulation, and even House method, which is going to make sense in this setting. And finally, one vague idea would be to generalize to analytic monad, which would allow the source specification to use some kind of structural congruence, which might give a new light on the transition system versus rewrite rules problem. Thank you very much for your attention.
Thank you, Tom. So we have time for some questions. Just raise your hand and I will bring you the microphone.
So you said that in your theory you could account for models by looking at T-algebras.
Yeah.
But then the T-algebras have to be objects of the transition category. Does that put a limit on the expressivity of the models you can consider in the theory? I mean, how have you looked at this?
No, I haven't looked at this yet. Probably it does, in a way. But I can't really say anything interesting, I think.
So a question on Slido. how could one translate a formalization of some programming language as a label transition system? And could this be used for type systems in general?
So for the first question, I guess the answer is this. If you come up with a source specification, then probably it gives rise to a monad on some transition category, which I think answers the question. And yes, typing, I should have mentioned it. Typing is a good question. It would be nice to also understand typing rules in terms of transition categories and prove abstract progress and soundness properties.
Okay. We still have time for one last question, or not?
Perhaps a basic question, but you're showing applications to like pi calculi. I mean, I assume you could also do like lambda calculus?
Sorry?
I assume you could also apply this to lambda calculus and functional languages, or?
I haven't done this already, especially because with lambda calculus, the standard notion of bisimulation is applicative bisimulation, which requires me to work on Howe's method first to prove that it's a congruence.
And that's on your to-do list.
Exactly.
Okay.
That's one of the next steps.
Okay.
So good question.
Great.
Okay, so let's thank Tom again.